Many of the terms we use to describe a solution are related to solubility. The solubility of a solute in a particular solvent is the maximum concentration that may be achieved under given conditions. We can call a solution saturated, unsaturated, and supersaturated. A saturated solution means that the solute's concentration is equal to its solubility. The solvent simply shouldn't be able to hold any more solute. All of the spaces between the solvent molecules have been occupied either by the ions of a strong electrolyte or by the covalent molecules of either a weak or a non-electrolyte. An unsaturated solution means that the solvent can hold more solute. So if you sprinkle some salt into a glass of water and you just have a pinch of salt, just a little bit, that solution is unsaturated. You can add more salt and the solvent will dissociate the solute. Now, an unsaturated solution can be further described as either dilute or concentrated. If it has a relatively low concentration, like a pinch of salt in a large glass of water, that would be a dilute solution. If you have an unsaturated solution with a relatively high concentration, so perhaps we're approaching a saturated solution, that would be called a concentrated. Now, we can create what's called a supersaturated solution if we change the conditions. For example, if you were going to be making like a simple sugar solution, you would heat water. By heating the water, you expand the spaces between each of the solvent molecules. That expansion allows more solute to be solvated. So this is a situation where the solute concentration will exceed its standard solubility. These are non-equilibrium states, and we'll talk more about equilibrium in the next module. But these are not stable at room conditions, and they will tend to, for example, if it's a solid in liquid, they will tend to recrystallize out. So if you were making, say, rock candy, which is really just recrystallized sugar, we use a technique in the laboratory called recrystallization, where first we make a supersaturated solution and then we allow the crystals to reform. It gets rid of any impurities that were in the solution. Now we can also have gases in liquids, and that particular example leads us to some specific solubility, some interesting solubility trends. So when we have a gas in liquid, the solubility of the gas in the liquid will decrease as the temperature increases. It's an inverse relationship. The corollary to that is what I just described with the supersaturated solution. As we increase the temperature of the solvent, we increase its solubility when we're talking about solids and liquids, and that's in most cases. Now for gases, as the temperature increases, the solubility of the gas decreases. So if you have an open bottle of soda on a warm day, the gas will escape much faster than if that soda was in the refrigerator. The pressure of a gas over a liquid will also affect the solubility of gas in liquid. So carbonated beverages, like soda, are often bottled with what's called a headspace of carbon dioxide on top. So you have your bottle of liquid and then you have a small space that is gaseous. That's filled with carbon dioxide in order to increase the pressure of the carbon dioxide over the liquid, because an increase in pressure will increase the solubility. That way you have a better chance of having the gas in the liquid when you go to open it. These two phenomena are also what causes a bottle of soda to, say, explode basically on a warm day. If you have a warm bottle of soda and the solubility of the gas has decreased because it's warm, and you open that soda, it's more likely for the soda to come splurting out the top. An environmental consequence of this phenomena is if you have like an industrial discharge into a lake or a river, and that discharge is very, very warm. That decreases the solubility of oxygen in that water. So unless there is a way to reoxygenate that water, it's not going to support much life. You can see this occur if you have a glass of cool water that you set out on a kitchen counter. You will see little bubbles form on the sides of that glass. That's because as that cooled water warms up, the gas is released because the solubility of that dissolved air decreases. Scuba divers are also affected by this phenomena, and it's the bends or decompression sickness. So as they're breathing their compressed air, which contains some nitrogen, because our air does contain nitrogen, then at depth, there's a whole lot more pressure exerted upon them. As they ascend or come back up to the surface, if they don't ascend slowly in order to re-equilibrate the gaseous bubbles, the nitrogen bubbles in their bloodstream, that gas will expand. Remember, it's also colder at depth. So these things together form decompression sickness. And these things together give us Henry's law. And here is the succinct version. The concentration of a gaseous solute in a solution is proportional to the partial pressure of the gas to which the solution is exposed. This relationship is called Henry's law. So in short, or even shorter, gaseous solutes will be more soluble when it's cold and when they're under pressure. A liquid-liquid solution is said to be infinitely mutually soluble. And these are called miscible solutions, when you have two liquids that are simply going to combine at any combination. So, for example, our antifreeze coolant is an example of miscible solutions. Ethanol and water are also miscible solutions. These substances will typically be polar substances or things that form hydrogen bonds. So, like your alcohols and water. Now, when we start getting into our nonpolar and polar molecules, when we start looking at things like water and oil, we have immiscible liquids. They're just not going to mix because we have the polar water that combines to form some hydrogen bonding. And then you have the non-polar substance of oil, so it only has dispersion forces. If you have a mixture of these two substances and it appears to be all one liquid rather than these two separate layers, then what you have is a dispersion, and that's different than a solution because the oil-water dispersion will end up forming layers after it sits a bit. Now, just to confuse things a little further, we could have some moderately mutual solubility, and that's called a partially miscible solution. So, as you can see here, we have our bromine water, and you have the two different compounds. On the left, you have bromine, and in the middle you have water, and then when you mix them together, they're partially miscible. You see the water layer that is on top is colored. There is some bromine in it with a darker layer of bromine underneath. And this is partially miscible because we have what's called a low solubility, and we'll quantify these things eventually. But this low solubility allows a little bit to be solubilized instead of a whole lot. And that also can be seen with solids in liquids. Now, in most cases, a solid in liquid will increase its solubility as the temperature increases. Now, again, for most inorganic solids. This is a general trend, and there are going to be exceptions. In fact, on this particular graph, there's an exception right here, this cesium sulfate. But for most solids, this is going to be the case. As temperature increases, solubility increases as well.